All right, welcome everyone. Thank you for joining us today. If you're new to our Science Speakers webinar series, we're glad you made it. We've had quite the lineup so far, featuring pioneering polar scientists educating us on their novel applications of remote sensing data. We had Dr. Mark Salvatore mapping Antarctic microbial mat communities from high-resolution imagery present in July, and in August we had Dr. Anna Liljedahl developing pan-Arctic imagery products via the Permafrost Discovery Gateway. And then just last week, Dr. Chun-Li Dai measuring topographic change caused by natural disasters such as volcanic eruptions and landslides from Arctic dam. And so it's a huge honor to continue our series with our longtime core user, Dr. Ellyn Enderlin. So first off, my name is Kathleen Torres-Parisian, and I'm a PGC user staff member, but I also lead PGC's educational outreach efforts such as this. So before we get started, I just want to share a few things about viewing the webinar in Zoom. All participants are muted throughout the webinar. So we will have time at the end of Ellyn's presentation for a Q&A. So feel free to submit your questions in the Q&A tab. And we are recording this presentation and we'll make it available on our website as well as our YouTube channel. So feel free to pop in, pop out, but you will be able to access this shortly after today's presentation. There we go. So before Dr. Enderlin educates us on her novel research using high-resolution data from PGC for iceberg analysis, I want to provide a brief introduction on the Polar Geospatial Center. So for those of you that have attended previous speakers' presentations, I apologize, as this is the same spiel, but as you know, I'll be brief. So we are the Polar Science and Logistics Support Organization at the University of Minnesota. And our core funding is provided by the National Science Foundation's Office of Polar Programs. We do, however, receive funding from additional agencies, including NASA's Cryosphere program. Our mission is to provide domain and institutional knowledge to solve a broad range of polar geospatial problems. So to provide access to some-meter commercial satellite imagery over the poles, and then the expertise to task, manage, and process that imagery and other high-level value-added products. And lastly, to provide educational courses and online materials to transfer our knowledge and experience to the community. So PGC's main products and services that enable our mission is really best described to fall into these four categories. We have satellite imagery, terrain models, digital maps, and geospatial support. So we have a lot of access, or I should say we have access to a lot of high-resolution sub-meter commercial satellite imagery from DigitalGlobe, talking petabytes. We have enough to cover over 95 Arctics and over 90 Antarctics, almost 6 times the surface of the Earth. So another major product and service PGC provides our terrain models. So elevation data is central to many science and logistics projects, and we've partnered with other public and private institutions to automatically produce freely available, high-resolution, high-quality digital surface models using the abundant DigitalGlobe imagery. So this data has endless potential, and learning how users like Dr. Enderlin apply Arctic Dem and REMA in their research is very gratifying and exciting for us at PGC. She's basically helping keeping us in business. So looking at the data repository, PGC stores and distributes polar geospatial data developed in-house and from external sources. At PGC, we know maps are not just pretty wall hangings, they're important tools. So we have hundreds of contemporary and historical polar maps searchable online in our map catalog, among other online geospatial databases. We definitely encourage you to check out our website. It's a fantastic resource for users and for our general polar enthusiasts. So please check it out at pgc.umn.edu if you're curious to learn more. It has exhaustive information about everything about PGC. So please check it out after Ellyn's talk. So looking at PGC's role to scientists, we have a breadth of users from the general public to Antarctic pilots to ornithologists to cooperative agencies. So for users like Ellyn, our role to scientists is essentially all geared to providing geospatial expertise to enable scientific objectives and hopefully to help users reach them more effectively and efficiently. So we spend our time processing and manipulating data so researchers can spend their time in their cool science. So a little more about this webinar series. Ellyn is our fourth science speaker, and I highly encourage you to check out our previous speakers' talks on our website. We are really excited about these, and we hope you will enjoy them at your leisure. So we've heard it too many times before, and clearly, I don't have to say this, but we're in unprecedented times, and many of us are working from home, and much of the Arctic and Antarctic field seasons have been canceled or altered significantly in some way. And so we're all just trying to find ways to adapt to that. So we thought this would be a great opportunity to showcase and connect our users through their research. Our users are leaders in innovative thinking and use remote sensing techniques to reach these far corners of the world in the Arctic or Antarctic that we can't reach right now. So we are absolutely thrilled to have Dr. Ellyn Enderlin as a science speaker today, featuring her work and ours. And we look forward to our closing guest science speaker, Andrew Fleming. He's from the British Antarctic Survey, and he'll be speaking on October 14th at 10 a.m. Central. So please visit our website or social media accounts for registration links and abstract. So without further ado, I'm pleased to welcome Dr. Ellyn Enderlin. She's a glaciologist and assistant professor in the Department of Geosciences at Boise State University. She has been a core user for our satellite imagery and elevation products for a long time now. Ellyn's research investigates a diverse set of processes between glacier-ocean interactions in both Greenland and Antarctica, coupling her remote sensing data and in situ data from GPS units her eggheads plant on glaciers. So eggheads is a highly favorable label. They're her students in the Enderlin glaciology group. I thought that was really cute. Ellyn, thank you for being here and sharing your work with us, our users, our friends, our followers. I'll let you take it from here.
Thank you. So I will go ahead and I'll share my screen, and you will very quickly see that I am also working from home. So my internet tends to be pretty stable, but I was saying earlier that I've had these weird issues where occasionally Zoom actually kills my computer. So if you miss me for about 2 minutes during this presentation, I apologize. I will pop right back on as soon as I possibly can. So thank you again for inviting me to give a talk. I'm really excited to be able to present on my research. And this is work that I started back when I was a postdoc at the University of Maine. So that was back in 2013. And then I stayed on there as research faculty for about 5 more years and really started to work on figuring out how we can best extract information from icebergs to figure out what's going on at glacier margins. And now I started my own group at Boise State, and I'm the Enderlin glaciology group. So yeah, my students are the eggheads. And so this is work now that my students have been picking up in the past couple years. I'm sort of passing off what I've been doing on to my students, and they're doing a really great job continuing this research. And so, like I said, today I'm going to be talking about iceberg elevations and specifically looking at elevation time series to see if we can use those data to provide insights into glacier-ocean interactions. And these icebergs are absolutely massive. I have some photos on this first slide to sort of provide some context here. This first one in the lower left is a photo that I took when I was in a helicopter in southeast Greenland. And at first you look and you see these little white dots out here in the ocean. You don't think anything of them. But if you actually look on this little piece of land that's sticking out, you can see little buildings there. Those are people's houses. And so these icebergs are house-sized or larger. So they're really quite huge. And I'm trying to look at these from space because, as you can imagine, if you're in this little boat right here, this is, I believe, a tourist boat. This was in Western Greenland. It's actually not very safe to be trying to collect observations from these icebergs in the field. They can roll over. If you ever see photos or videos of people that are like right up against a glacier or right next to an iceberg because they're on some sort of tourist cruise, that's not a very safe place to be. And so I prefer to be looking at these icebergs from the air or from space. And so today I'm going to provide a little bit of background on glacier change to start us off, because ultimately I am a glaciologist and I'm using these icebergs as a tool to infer what is going on at the glacier boundaries. And so I'm really interested in, you can see this little GIF I pulled from online. I'm trying to figure out what is causing these calving processes that you can see here. Is the ocean triggering that? Is the ocean influencing that in some way? And the icebergs are my tool at getting at that question. So I'll give you some background on glacier change, specifically on terminus ablation, which is this iceberg calving and also melting below the waterline. I'll talk a lot about, obviously, remote sensing of icebergs, the work that I've been doing using PGC data. We'll talk about these iceberg melt rates I've been able to extract. Also, iceberg meltwater fluxes, that's really the volume loss from icebergs. That's what oceanographers are primarily interested in. And then also about, can we possibly use icebergs to study controls on iceberg calving? And so to first provide some context, like I said, I am a glaciologist. So I'm really interested in glaciers. And for those of you who aren't that familiar with glaciers, I always show this in my intro classes. This is a great tool by the University of Colorado that you can go in here and make these nice little videos where you can show students what it looks like to have a glacier flow. And so in this video, you can see what I just did was I believe I changed the amount of snowfall. So this white area here is increasing. So we're increasing the accumulation that's driving flow out towards the ocean or down towards lower elevations here. You can see the little rock particles moving to show you there's flow. And then I changed the temperature so it's warmer, and that caused the glacier to recede. So we had an increase in ablation, which is largely surface melting for glaciers like this. So I'm interested in these guys. I'm particularly interested in glaciers that flow all the way out into the ocean, unlike this little mountain glacier that you can see right here. But really, glaciers are found anywhere around the world. They form anywhere where you have snowfall that exceeds melting. So in the map you see in the top corner here, all the blue areas on that map are showing you the locations of glaciers. And you can also see that there's all this blue here around Greenland and then a big white blob right in the middle. That's the ice sheet. So that's technically not a glacier. It's land ice, just like glaciers, but it's much, much larger. And it has glaciers that drain it out to the ocean. And we have the same situation down here for Antarctica as well. Antarctica is made up of 2 ice sheets and also has lots of glaciers that drain these ice sheets to the ocean, as well as smaller glaciers along the Antarctic Peninsula. And so the glaciers that I'm particularly interested in are these marine terminating ones, the ones that make it all the way out to the ocean. Not every glacier does that, but those are the ones that to me are the most exciting and the most interesting because they respond really sensitively to climate change. That's not to say that land terminating ones don't. We see that those have actually been changing quite a bit in recent years as well. But these marine terminating ones are really, really sensitive to climate change because they're being melted along their surface. So if we increase our air temperature, we're causing melting at the surface here. That's surface ablation in my little cartoon. But also they're being influenced by the ocean as well. So it's a 1-2 punch. They get the ocean warming is also causing these glaciers to retreat or recede. And so that's really important as well. There are 2 different warming components of the Earth's climate. that are causing these glaciers to change their behavior and to shrink. And so they're really sensitive to both of these different environments. Also, their flow is really, really fast. So I'll show some estimates of ice flow later on, but these glaciers are moving at up to tens of kilometers per year. And that's really fast flow. That is not all due to deformation. Ice just will very slowly deform and sort of ooze out towards lower elevations, just like honey deforms. It's a viscous fluid. But these glaciers are also sliding along the rock beneath them. And for these marine terminating glaciers, they slide really, really fast because they have high water pressures maintained beneath them. And so that way they slide really quickly. This is a very effective slip and slide that's going on. So these glaciers, not only are they responding both to air and ocean warming, but they can respond really quickly because they have these really fast dynamic changes that go on in their flow. And now I'm really interested in right where these glaciers meet the ocean. And so I want to see what is going on in this process that is called terminus ablation. And so that is the combination of submarine melting, that's melting below the waterline, and also iceberg calving. And in my cartoon that I have here, you can see I'm not the greatest person at making cartoons. I'm definitely not proficient in Illustrator or anything like that, but hopefully you can get the message from these that the ice is flowing from right to left, and the glacier is moving out here towards the ocean. And what we see here is that we have blocks of ice breaking off, that's iceberg calving, and then you see those icebergs are floating away. And then we also have melting going on beneath the waterline here. And this is the process, well, actually both of these processes are really difficult to understand. Because like I said before, imagine you don't want to be in a place where an iceberg could calve off at any given point. That's a really dangerous location to be making observations. You also don't want to be on the glacier surface at that point either, because is going to occur. It's like trying to predict an earthquake. And so you don't really want to be right there because that block of ice you're standing on could just break right off. So we have really limited understanding of these processes that are going on, but they're really critically important. Because if the terminus ablation is faster than the rate that ice is flowing out towards the ocean, then the glacier terminus retreat. And so the terminus retreat is really important because people always describe this as, it's like letting a cork out of a bottle. It causes the ice behind it to flow at faster speeds, it accelerates. I like to think of this more like you're losing a dam. So just like dams hold back water, they retain water at these high elevations. And if you blew up a dam, all that water would come rushing out due to the effects of gravity. That's the same thing that goes on for these glaciers. These are essentially little ice dams right at their terminus. So that ice at the terminus is providing friction, providing frictional resistance where it's in contact with the rock walls along the sides and also the bed beneath it. And so when you remove any of that ice from the terminus, you're essentially removing this ice dam. And that causes all of the ice at higher elevations behind it to accelerate and to flow faster out towards the ocean. And we call this changes in dynamics because this is influencing the stress balance for these glaciers. And so that's what I'm really interested in here. And this process of submarine melting is actually really quite complicated. So is iceberg calving. We know that obviously calving has to involve fractures of the ice, and then that ice has to move away from the terminus. Right? So we know that, all right, if we fracture the ice more, that might increase our terminus ablation. We also can do things like pump more water into these crevasses, and that causes them to fracture deeper. So that will cause that to move away, break off, move away from the terminus. But we can also, if we warm our air temperatures, some of that water gets down here to the base of the glacier. That's what I have labeled as subglacial discharge here. So not only is that causing that nice slip and slide effect that makes these glaciers move so quickly, but that is also coming out at the terminus here as buoyant, really cold and fresh water. And when that water comes out at the terminus, it draws in this warm, salty ocean water that's at depth, these subsurface currents here. And that causes melting in all these places what you see in red. We can also just warm the ocean, and that would accomplish the same thing. And in either case, we start undercutting the glacier here, and again, that influences calving. So you can see not only is it really difficult to make observations, in situ observations right at this location, it's also really complicated processes that are going on here where we have feedbacks between iceberg calving and submarine melting. Warming the atmosphere can cause lots of different things, and so can warming the ocean. And so it's really difficult to disentangle all of these processes. And this is really important because we know that terminus ablation has increased. So here I'm focusing on Greenland, but this is true for glaciers pretty much globally at this point. But here I'm showing some results. This was actually work largely led by an undergraduate, Alex Eddy, who was in my PhD advisor, Ian Howitt, his group when I was a grad student. And Alex spent several years doing really painstaking mapping of these glacier terminus positions and satellite images. So she went to all these glaciers all around Greenland that you can see these symbols here and mapped glacier terminus positions in satellite images, particularly Landsat images. And what she found is now we have them broken into decades here. The symbols are just showing you where we actually have data for each different decade. But then we have these bar and whisker plots over here. And these are showing you over these sort of decadal time periods, the sort of bulk area, the aggregate terminus position change for each one of these regions. So I have them blocked off here in colors. So the blue block here, the light blue is in the northwest. The sort of darker blue, actually I have it in the wrong spot here. It should actually be down on this block down here. It should be the southwest. And then this orange one here is the southeast. And so what I want you to see in these is that it actually in all of these regions, you can see that in the 80s and the 90s, those are those sort of the 70s into 80s and 90s, those are those first two bar and whisker plots in each one of these, that the glaciers weren't really retreating very much. They were pretty stable. So that means that their terminus ablation and their ice flow speeds were equal to each other. And then once we get into the 2000s, you can see all of these sort of start to stretch out. And that's showing you that we have terminus ablation exceeding ice flow in these locations. So the glacier termini started to retreat. And we can see that pretty much globally. All right, 80s and 90s were pretty stable. We get into late 90s into the 2000s, the glaciers really started to retreat all over. And to show you a little bit more of what this looked like, this is showing some glaciers that I looked at actually for my master's. My maiden name is McFadden, so this is from a paper I put out for my master's degree here. And these are showing you two glaciers that are in northwest Greenland. And here are some Landsat images of those glaciers from 2000. And I have delineated where the glacier terminus was for those two. And then these are elevation profiles shown in sort of this middle panel. So it's like a cross section of the glacier. And I have a red arrow here just pointing at, of course, my colors aren't the same between my figures because that would make sense. But so I have a red arrow showing you where the terminus position was basically in 2000. And then I have speed time series shown here on the rightmost set of panels. And the red symbols are showing you the annual averages, and the blue were all of the observations that I had for those time periods. And so you can see here that the glacier terminus was pretty far out, and you get an idea for that when I go to 2009. And this is when Landsat 7 had the scanline corrector failures. That's what you see are these weird stripes in here. But you could still map the terminus position, and you could see that there was quite a large amount of retreat for both of these glaciers. And I have, again, that arrow shown here now for both of these where the glacier terminus was in 2009. And I want you to notice how much faster these glaciers were flowing in 2009. And so what happened is there's some variability from glacier to glacier, but what we see is that these glaciers started to retreat and they accelerated because they lost that sort of ice dam that was at their terminus. And this acceleration is quite a bit. I mean, this glacier was flowing 3 meters per day and went up to about 8 meters per day. So that's a huge increase in speed. And that retreat has actually continued. So this just went through when I did my master's degree. But you can see that these glaciers, again, have continued to shrink. And what does this mean? So what we have seen is that all of these glaciers have increased their iceberg discharge. And that's what's shown on this time series here. This is a really nice data set by Ken Mankoff. He published this in Earth System Science Data. It is a data set that gets continuously updated. All of his code is shared, and it is estimates of iceberg discharge coming from all of these glaciers all around Greenland. So he has those all drawn here in this little map. And then these are regional trends that you see in this time series. And again, if we go back to the 80s and 90s, they were pretty stable. And then once we hit the 2000s, when this terminus retreat occurred, these glaciers accelerated and they started to increase their iceberg discharge. You can see that really nicely for the purple, that's the Northwest, where I was showing you those example glaciers before. So this has happened globally. I'm just showing Greenland here for simplicity, but this has happened all over the world. We see this in Antarctica, we see this in Alaska, we see it in Svalbard in Canada. There's been retreat, acceleration, and mass loss from these glaciers. So what's actually causing this? And like I said before, it's really hard to disentangle all these processes that are going on right at the terminus. We know that the air temperatures are warming. The ocean temperatures that we have, subsurface temperatures, also show us that's warming as well. But it's really hard to tease out how important is the ocean at driving these terminus changes versus changes in air temperature. And so I'm really trying to get at what is going on in terms of ocean forcing of these glaciers. And so I'm interested in this submarine melting component. And places where we have floating ice, so I show Antarctica for this, because Antarctica is one of the places where we have really massive floating ice shelves. They don't really exist for Greenland or anywhere really in the Arctic anymore. Some have existed far north in Greenland. There's still a couple left, and in really high Arctic Canada, but even those are collapsing now. But in these places around Antarctica where we have ice shelves, those are all these sort of colored areas with reds and blues all around here. And if you look at those, what we can do is we can look at changes in their elevation either over time or in space. These are the Eulerian or Lagrangian approaches for doing this. You can look at these changes in elevation and use that to say something about how quickly they're melting from below. So you can estimate these submarine melt rates from elevation changes. And this is a really great data set that came out this year where they're actually doing that. It's over at least a 20-year time period, I believe at least 30 years. So there's a great time series now of these melt rates for Antarctic ice shelves. But the problem is, like I was saying before, is we really don't have very many ice shelves left. So we can't look at submarine melting for these places using ice shelf elevation changes. And so when I started my postdoc, that really got me thinking. Under the supervision of Gordon Hamilton, he and I sort of talked about this and we said, well, why don't we look at icebergs instead? And it really got me thinking, could we actually do that? And this is really when the WorldView data just started to really become like popular and started to really come out and become available to the community. And so I said, all right, let's start looking at these WorldView data sets. Let's look at elevations that we can get from these high resolution satellite images and see if we can tease out iceberg melting from that. So I'm looking at their elevation changes to get at how quickly they're melting. And the reason why you could say, okay, I can look at iceberg melting and use that to infer glacier melting beneath the water is because they're both related to the ocean temperature and the shear of water moving past them. And so these things still need to be disentangled a little bit, but that means that both the icebergs and the glaciers should be subjected to the same sort of ocean forcing conditions. And what we can do is we can look at really nice elevation maps like I have here. This is for Thwaites. This is down in Antarctica here. These are all icebergs that have broken off from the glacier terminus, which is right over here in this DEM. I'm sorry, I do not have a color bar on this, which I didn't realize until pretty late, but these icebergs stick out about 50 meters out of the water at their highest elevations. That's where it's saturated on here. And what we can do is we can look at these individual icebergs, like this one right here in the middle, and we can look at their elevation changes over time. So that's my dz dt in this equation. And since they're floating, I can use the contrast in the density of seawater and ice to convert that surface elevation change to a thickness change. That's my big dh dt here. And then if I multiply that by the surface area of the iceberg, that gives me a volume change over time. So that is my meltwater flux. And these elevations, like I said, are extracted from WorldView stereo images. And so they're used to make these digital elevation models, like you can see here. Sorry that these are earlier figures, they're not very colorblind friendly. But what I want you to see in these is that here we have this one large iceberg in Greenland from July 2nd of 2014 and the corresponding DEM. And then we have another one from July 31st and its corresponding DEM. And you can see right away in these two, they have the same color bars and that there's a lot of red in this top one and mostly yellow in this lower one. And that's showing us that surface lowering. And that is what I can use to come up with my volume changes. Now it's also really difficult, and I show these zoomed in images because you can see these icebergs aren't just sort of floating out there in a nice dark ocean where you can really easily pick them out individually. They're in this really densely packed matrix of icebergs and little bergy bits, little bits of icebergs that have broken off. So you can't really pick them out easily. And it's really hard to automatically track them as well, because not only do they move along the fjord, but then they rotate. And so if you're just trying to use something that's like feature tracking, so looking at image correlation over time, it's difficult to handle the fact that they're rotating. So if they rotate, they might not show up as being the same iceberg in your algorithm, but they really are. And so it's really difficult to distinguish these individual icebergs. And so this has been largely a manual process. And it's also been really impeded by the fact that I'm sure if everyone here is a WorldView user, you know that you can task the satellites, and PGC does a great job of that, but it doesn't mean you always get the images that you want. So I have been trying to task satellites now for years of like monthly stereo images for these glaciers. Even when that happens, there are clouds. And so you don't always get what you need. So we need to be able to manually track them, and we need to have enough time separation between them that we can resolve those elevation changes, like you can see here in these examples that I have, but short enough that the icebergs don't break up or roll over, or we otherwise just lose them. We just can't track them in between. And so here's an example of when sometimes it works and sometimes it doesn't. Again, this is for Thwaites, and these are some images just from this past year. And you can see these large icebergs out here. I mean, these are absolutely massive. They're like 2 kilometers across. And this one here in orange, okay, you can easily pick that out in both of them. And quite a few in these are the same. But then this one I have up here in red is showing you, well, that one fragmented. So you can't use that one for this analysis. And the reason why this is really great is we can get these meltwater fluxes over time. But then there is a little bit of uncertainty in converting these meltwater fluxes to melt rate. So the melt rate is essentially, it is this amount of mass that you're using. It's ablation horizontal or orthogonal to the face of the iceberg. So that's what this arrow is trying to show you in this photo I took in Greenland. So imagine the ice used to extend all the way out to here. And so we're trying to figure out how quickly each one of those faces is ablating, how quickly it's melting. So we take our meltwater flux that we can get from looking at these elevation changes over time, and we divide it by the submerged ice area. And these area estimates are really uncertain. I use really simplified geometries for this. You can see though that the geometries are really complex. We can't infer these from surface observations, and they have varying complexity. So really ultimately, we know that when we're converting to the melt rates, our melt rates are always using surface areas that are too small because they're too simple, but we can't tell what that bias is. So we know that it's a bit of an overestimate, but it's really hard to discern exactly what that bias is for each individual iceberg. So this relies on looking at a decently large sampling of icebergs to then figure out, okay, what are our melt rate patterns that we see? And hopefully that'll cancel out some of these varying uncertainties that we have in our melt rate estimates. And this is showing you a paper I put out. This was largely work by one of the undergraduates in my group at UMaine. She delineated literally hundreds of icebergs around Greenland over several years to come up with these maps you can see of these iceberg positions. And then these time series we see of meltwater flux plotted along the y-axis versus the submerged area plotted along the x. And in all of my figures, I try to arrange them geographically so that basically if you started up here and this is the northwesternmost site, and then if you went counterclockwise around here, you'd be going around the southern tip of Greenland and then back up the east coast here. And these little M's I have up here in the corner, those are showing you the slopes of these best fit lines. And those are approximately your melt rate for each location. So if we look at those, we can see that the large scale variations in iceberg melting pretty much match regional ocean temperature patterns. In the southeast, down here, we have this warm Erminger current that comes in contact with Greenland, and that's where we have high melt rates here. And those are pretty high also when we go up the west coast here. And then once we keep going farther and farther north along the west coast, those melt rates decrease. And up here in the northeast, we have the lowest melt rates. That's where we have this cold, cold water coming out from the Arctic Ocean around the Greenland coast. So this was really great result. This showed me this method has a lot of potential because it does actually show us tell us something about the ocean temperatures around coastal Greenland. And when I got into these data even more, I thought this was particularly promising because the patterns that we see with iceberg melting with depth match what we expect based on independent estimates made with in situ ocean observations and models. So now these plots are showing you the area average melt rates, that melt rate orthogonal to the ice face. And then the x-axis is iceberg draft. So that's just its depth below sea level. And so I have all the time series shown here. These are averages for all of the icebergs. And then at the top, these have been normalized just so that they're stretched from -1 to 1. And what you see in this, particularly in the normalized one, is I hope you can see that these melt rates in the first 200 meters are generally lower than those below 200 meters depth. And that matches exactly what we expect from in situ observations of ocean temperatures and then modeled iceberg melt rates for Greenland. So here are some in situ ocean temperature observations. I've rotated everything sideways. This is work by Twyla Moon. She put out in Nature in 2018. Rotated these sideways just so they're sort of showing the same orientation as my graphs. And this is showing you the ocean temperatures here. And so you can see, particularly in the winter months, the water is cold up near the surface in this near surface layer, and then much warmer at depth. And you can see that reflected in her iceberg melt rates that she modeled here. They're lower near the surface and increase dramatically with depth. And those are the same patterns that I see in my iceberg melt rates as well. And so this is really promising. This tells us that we can resolve differences in ocean temperatures or an ocean forcing of these glaciers in the near surface layer and also in the subsurface. And this is really important because these glaciers, a lot of them go deeper than 200 meters. And so we can't really get any observations of these subsurface ocean conditions unless we go collect in situ ocean observations. So this is a great way for us to start to say, okay, this is how these ocean conditions vary, where that warm, salty subsurface water is coming in contact with the glaciers. And now this work has been expanded over the past couple of years. At UMaine, I had an undergrad and a graduate student working on this, and now I have an undergraduate working on this at Boise State as well, where we've expanded this work to look at Antarctic iceberg melting as well. And again, these are sort of geographically arranged, where we're starting along the West Antarctic Peninsula. You're going counterclockwise, you're going along down to West Antarctica, and loop around to East Antarctica and come back to the East Antarctic Peninsula up here. And those letters are shown here in this map. And what I want to point out is that these iceberg melt rates also generally follow regional ocean temperature patterns. I'm not going to get into the nitty-gritty here that we do see lots of deviations in Greenland and also in Antarctica as well. And those tell us something about local alteration or the inability of these warm subsurface waters to get to the glaciers. That's really important as well. But just to demonstrate here that this is sort of what we can get out of it. So if you look at this map over here, the red shading is showing you warm waters along Western Antarctica. And so we're focusing on this red here and all of these panels here on the left-hand side. And note that this is the melt rate, and it goes from 0 to 18 centimeters per day for West Antarctica, but it's only 0 to 3 centimeters per day for East Antarctica. So we see that the melt rates are considerably higher in these places where we know warm ocean currents penetrate towards the glaciers. So we see this, again, this good agreement with regional ocean temperature data overall. But I also want to point out, we see in Antarctica that the melt rates are way smaller than what we get in Greenland. So if Greenland, we're looking at melt rates on the order of meters per day. Here, centimeters per day. So even our melt rates that are the highest in Antarctica are about comparable with our lowest ones we saw in Greenland. So this is also really interesting to compare, tells us something about the importance of submarine melting in these two different systems. And this is something that's really cool that my students and I have been looking at recently, is that as we start to add to these data sets, we're seeing here now in Antarctica that the icebergs might also tell us where there is subglacial discharge coming out from the base of these glaciers, which really influences how quickly these glacier termini are melting. And so we can see that here, this is for Edgeworth Glacier along the East Antarctic Peninsula. There stands out this really, really weirdly high melt rate here in this orange reddish sort of color. I believe that is where there is meltwater that's coming out from the base of the glacier. All the other melt rates are a lot more sort of comparable to each other. And we also see that here, this is for Thwaites again. And so this is that area where I was showing you those example images in DEMs earlier. And what we see is in this area that's really close to the glacier margin, so the glacier is flowing from over here on the right out towards the ocean, really close to the glacier margin here, we have very high melt rates. But as you move away from the glacier, our melt rates are less as that subglacial discharge disperses. And again, this is really important because the subglacial discharge influences our terminus melting. It also is really important because it could potentially tell us there is actually subglacial discharge coming from Edgeworth Glacier, where it really is not predicted by atmospheric models right now. And then finally, we found my master's student who finished last year, Mariama Dryack. She and I had a paper just come out this past year that showed that these spatial patterns in iceberg melt rates correlate well with that terminus ablation, or frontal ablation is what we called it in this paper. And so this is showing us that, again, there could be a really strong link between variations in this melt forcing of these glaciers and then how quickly their terminus positions are changing over time. And I'll briefly talk about iceberg melt fluxes here, and then I'll talk about also the applications to studying iceberg calving to wrap up this talk. So I focus primarily on these melt rates because to me as a glaciologist, that's what I really care about. I want to know what is going on that's influencing these glacier termini. But for oceanographers, they care more about these melt fluxes because these are freshwater fluxes going into the ocean, which may influence the circulation near these glaciers. And I can directly get meltwater fluxes by doing this elevation differencing for individual icebergs. But I'm not going to go in there and have some poor undergraduate delineate every single iceberg in this and then find it again at some other time and then measure that change. That would be horrific. And you can't even do that for some of these really tiny ones. Like, you just can't pick them out. So that is not a feasible alternative. That's not a feasible approach for this. So what I do is I actually use these elevation distributions that you can get from the DEMs to come up with iceberg size distributions. And so this is always when people like really scratch their heads, and hopefully this is like a decent explanation of it. But what I have done is I pull out these elevation histograms like what I have shown here for this example DEM. This is back up in Greenland. This is for Sermilik Fjord, which drains Helheim Glacier out towards the ocean. So the glacier terminus would be right here. You can see these really large icebergs that have broken off from the glacier. And so I pull out these elevation distributions, this histogram shown here. So the count is the number of pixels in each elevation bin. And I can take those elevations and I can convert them to thicknesses. And that's what I did before. This is just using the contrast and the density of ice and seawater. So I can get a thickness. Well, we know that these icebergs have characteristic aspect ratios. That's width to thickness ratios. That if they exceed a certain ratio, they will tip over. And you can get these aspect ratios from satellite images, and they're always around 2. And that has now been confirmed with some in situ sonar observations of iceberg geometries as well. So what you can do is convert these thicknesses to an estimate of width. And then from there, I use a really simple geometry, and I can come up with an average area of each iceberg in each one of these little elevation bins. So to give you an example of that, you can see I have down here, I say a 3-meter elevation bin equals about 28 meters of thickness, or about 56 meters wide. And that would be each iceberg in that bin has an average area of about 2,505 square meters. Well, then I know the number of pixels that are in that bin. I know the footprint of each pixel. These are 2-meter resolution DEMs. So I can combine all of that information to come up with a number of icebergs that corresponds to that sort of elevation bin. And these icebergs aren't like perfect and they don't all fall in one elevation bin, but this has proven to be pretty effective, that this gives you these elevation and then size distributions of icebergs in these fjords. And so all I have to do then is I, again, come up with a submerged area. I use these simple geometries for each one of those iceberg sizes. And I multiply by the number of icebergs, and then I multiply by the melt rate. And so when I do that, I come up with this meltwater flux for the whole thing of ice. So all of those icebergs and all the little bergy bits you can see, those, I get an iceberg meltwater flux from all of them. And I did this for 2 locations in Greenland, and I'd like to expand this work in the future. And I have found that the iceberg meltwater fluxes actually are the dominant source of fresh water to these fjords throughout most of the year. So it's really, really important when the subglacial discharge, when all the melting from the glacier turns off in the winter, these icebergs are still there melting. And that's really important in terms of controlling the oceanographic properties of these fjords. I also found, if you look at these plots that I have here, that the meltwater fluxes vary strongly with the shallow iceberg melt rates. And that makes sense because most of the little bits of icebergs, it's mostly like lots of little bits with then some larger icebergs embedded into it. So that makes sense that the shallow melt rates are really important. And that it also varies with the ice extent. So if you have more ice that's sitting in there, it's like if you have more ice in your drink, then you have more fresh water that's coming off of those pieces of ice. So this is really important because this tells us that these meltwater fluxes will vary with our ocean conditions, okay? That's what I've been trying to get at. It'll also vary with the iceberg volume, so the total volume of ice, but it'll also vary with how broken up those little bits of ice are. So you can imagine if you have lots of little bits of ice, they have a very high surface area to volume ratio, and they melt really quickly. That's why slushies melt really fast, but if you put ice cubes in a drink, they don't. So they have, if we change our calving style to suddenly break off lots of little bits instead of big ones, we might also be influencing when and where we're putting fresh water into these local environments around these glaciers. For the sake of time, I'm not going to show this. This is a video recorded of Helheim Glacier calving, which, well, I guess it's going to show anyway. It's just showing us that there are these, you can see all these pieces of ice that are out in the fjord, and they're highly variable in size. And then you can see this massive piece of ice break off here. And so I'm also interested in understanding to figure out how it affects the glacier behavior and also how it affects these iceberg size distributions. What is going on with these calving processes that we see? And so I started looking at these WorldView DEMs that I have for fjords. So this is that same fjord. This is Sermilik. Again, this is the one I showed you before. The glacier would always be over here on the left. And you can see that this one from March of 2011 looks a lot different than the other ones. Just like qualitatively, you can inspect it and say, wow, that's sort of weird. It's all very dark with just like a bunch of big icebergs, whereas these other ones have much more of like a medley of different sizes. So we don't know that much about what controls calving. I mean, we do, we know some of it, but we don't get all of the nuance that's going on. And so I started to think, well, could we use these size distributions to actually tell us about the calving process? And this is really preliminary work that Jan Austrom contacted me about looking at iceberg size distributions about a year or so ago now. He created a applied fragmentation theory to look at these size distributions and understand what is dictating fracture, or what is dictating the calving process. And here is an example that he has here. These theoretical curves show you that if you have lots of branching fractures that all come together, you would end up with a size distribution, so number of fragments versus the size of them, that looks like this orange curve. And if you have something that is those huge, like we just saw for that Helheim video, these huge tabular icebergs that break off and float away from the terminus, you would end up with something that looks like this cyan theoretical curve here. And so when we actually look at our data, that's what I have shown here. Those are from those DEMs for Helheim. We see that this light blue one, this cyan one here, really stands out. That's that winter one that I said looked a lot different too. So it actually has a very different size distribution. And if you throw those curves up on there, you end up finding that icebergs greater than about 0.1 kilometers squared in area were dominated by calving of these uncorrelated fractures. And everything else was from these branching fractures. And that was our only sort of winter observation. The other ones are all summer, and they're all dominated by those branching fractures. So this is just really preliminary work, but this suggests to me that we can start using these iceberg size distributions and this fragmentation theory to have a quantitative way of saying, these are the different processes that are governing iceberg calving. And that's really important because, again, that will influence when and where that meltwater from the icebergs gets out into the ocean. It also influences the sort of dynamic response of the glacier to changes in terminus position. So in summary, what I really want people to understand is that the glaciers basically globally are retreating because of changes in ice-ocean interactions. It's really hard to figure out what exactly is going on at a place that looks like this. Again, this is Helheim, and you can see here all of this ice. You can't get a boat in there. And this cliff is like about 80 meters tall. And I was in a helicopter where we try to go collect ocean observations from this little plume that's sticking up right there. That is a scary place to be. So we can't really get observations on the broken up ice of the glacier surface. We can't really get them out from the ocean. Remote sensing offers the best methods that we have to figure out what is going on here. And looking at these iceberg elevation distributions has really given me the ability to start looking at them, seeing if we can use them as a proxy for ocean conditions, looking at the meltwater fluxes, which is important for the fjord circulation, and also starting now to see if we can actually tease out something about calving from these data as well. So they're really, really valuable resources for understanding a really critical interface between glaciers and the oceans. And with that, I just would like to thank my funding. It's largely come from a series of NSF grants that I've had to explore this research. And I encourage you that if you're interested in hearing more about it, you can check out my website I have for my group here. I'm always trying to keep that pretty up to date. And also you can check out my department's website as well. So with that, thank you for your time, and I'm happy to take any questions that people have.
Thank you so much. I hope everyone has enjoyed you explaining these really complex processes and yeah, I think we can start off with the first question here that asks, can you use the same DEM images of the Himalayas to measure change in glacier melting?
Yes, you actually can. Sorry, my mouse also like vanishes on my screen sometimes and I can't find it. Yes, you can. And actually I saw earlier that Dave Sheen was one of the people that had joined as a participant on here. Dave actually does look at that quite a bit, where he looks at using these DEMs to look at elevation changes of glaciers in mountain regions over time and figuring out what that equates to in terms of glacier mass loss.
Great, thank you. Another question. Great presentation, Ellyn. Do you see potential for planet imagery being integrated into your research? And what implications would that high frequency planet imagery have on how you track and study icebergs and glacier behavior?
That's a great question. That is something I have really wanted to look into and have not just had the bandwidth to do it yet. I believe Lee Stearns, she's at Kansas. She has been doing that a little bit now. I have found that in looking at planet imagery, it's a little difficult because it at least used to be really saturated in the polar regions, at least when you were trying to like preview it. And so it was difficult to figure out what you were going to get out of those data. I think it was just that way because the polar regions just happened to be super duper bright and they had it saturated, like not for polar people. But I think that's it's a really interesting idea, because that would provide the opportunity to potentially track icebergs with similar spatial resolution, but much higher temporal resolution. So you don't have to worry so much about that rotational component of them.
Awesome. Yeah, I think they've been working on the calibration for that. See, we have another one here. Thank you, Ellyn, for the fantastic presentation. Very exciting work. As an iceberg modeler, I'm very happy to see iceberg observations happening and generating data for us to improve our models. Not a question, but thank you so much. That's very kind.
Yeah, and icebergs were definitely something that I felt was like really overlooked in terms of actually if they can provide any really important information. And I do have a proposal out right now to see if I can map their freshwater flux distributions a lot better, because I feel like that is incredibly important. And it's something that we really simplify right now in ocean models, is like the ice leaves Greenland and then it just goes in the ocean, and glaciologists don't tend to care about that. Mm-hmm. But it's something that is sort of like, it's not really the oceanographer's job either. So I'm hoping that this sort of like bridges those two different fields.
We have another question. What are your thoughts on doing large-scale iceberg delineations everywhere with machine learning pipelines? Any efforts in that direction?
Yeah, so I have a student who she has been applying an automated method. It's the WTMM method, so what wavelet transform maximum modulus method, which is an automated image processing method to sort of start to resolve boundaries. But largely we've been looking at this boundary between the glacier interface, so the glacier terminus here, even in places where you have this ice melange, all of these icebergs out here. And so she's had a really great success with that. And you can actually also use the same pipeline that she's been working with to then map icebergs. And we have found it works in some places. You can find like closed polygons from that. But it is still really difficult that we just have so many like little fragments that it's still really difficult to pick out all of those like individual fragments in the imagery.
Mm. Just checking to see if there's any more questions. I think we can wrap up now. Thank you so much, Ellyn. I think it's really exciting for all of us and all of our followers to hear all of the potential that you've unleashed with learning about icebergs and the ice-ocean interactions. And it sounds like there's a lot of potential in the future for your career, and we're excited to hear from you and what you come up with in your future. So thank you so much for sharing.
Yes, thank you.
in your research. And again, thank you everyone for joining us today. This recording will be available on our website as well as on our YouTube channel in just the coming days. So thank you so much, everyone. Have a great day.